Okay, so I'm really pleased to be here, but I'm also terrified, just like this is a disclaimer. The title of this talk is very long, and there are two things that are really important, but I think the most important will be open source. Everything that I will say now will not work for closed source for one simple reason, which is called the golden sample, and I will come back to it. But before, I will do a very short introduction. So no, I'm not the French legend. I'm Olivier Thomas, founder and CTO of TechSplain. I wanted to give credits to the team because the work I will present, of course, is from them. Feedback, no? Anyway, what we do at TechSplain? At TechSplain, we take chips apart, okay? So we slice the chips in little pieces to reach all of the layers. But we take also like the pictures of all of the layers because we want to convert basically pictures into circuit diagram. And that's what we do. So that's how it looks at the end of the day. Because if you can do this, you can do a number of things. And I think ICs are pretty cool to look for. And you will say, oh yeah, he's the hardware guy. But the hardware guy, yeah, it's just making a funny feedback. Do you want me to take like the...
Get closer to the microphone. Oh, it's the hole.
Uh-huh.
Oh no.
I break chips usually, but yeah. Let's do this. Interesting. Okay, good. It's back. So I will do with the mic now. Fine. So yeah, you will say I'm a hardware guy, but usually hardware guys like me are used for one simple reason: extracting firmware. All right. So I was giving a ROM dumb training at the conference, and that's one thing we do, of course. So we do ROM, but we do all types of NVM. And the thing is, we can analyze netlist. You know. So if you can analyze a netlist, basically. You can extract NVMs, so it can be flash, encrypted flash, or you name it, you know, memories in general. So that's all we do at TechSplain because we can do IC reverse engineering. Yeah, so it's pretty broad, but I will talk only about one thing. How we do it? So we have a lab, so we use chemicals, wet chemicals, dry chemicals. We do CMP, so polishing, to make a simple word. We use SEMs. You should all buy an SEM. No, but if you have the choice between a nice car and an SEM, I don't know, just saying. Because you will make pictures like this and they are looking cool, okay? And that's pictures, examples of pictures of all layers of an integrated circuit, basically. And then, of course, this is a circuit diagram of a very tiny chip. Okay, this chip was very small. It was one of the first netlists that we printed on paper for fun. The other ones are way too big. So anyway, if you have the netlist of a chip now, if you have a focused ion beam, so this time it's more than a car. You will be able to modify the circuitry basically. And if you can do so, well, you can modify it, okay? You can prepare it. So if you want to do wire bonding, Alex is doing it in the other room after the talk. A bit after the talk. And then what you can do is microprobe, basically. So that's invasive attack. And if you can do this, usually you can extract a lot of targets. Anyway, we use a tool for this, which is ChipJuice. ChipJuice will convert pictures to circuit diagrams. So it will work on digital circuitry mainly. You extract features, you stitch pictures, you extract standard cell libraries of chips. People will not like it. And then basically you can reconstruct the full stack and get to the circuit diagram and the mask set of the chip. So the motivation for me is pretty simple for the talk. I think silicon chips are a strategic asset because everywhere handling your data, I mean you name it. So I think we should be careful. And I will talk about hardware backdoors. And for me, the starting point was Arshin. So Arshin is a European project. So this is why I have to put the logo and everything. It speaks about open source hardware and software, but you see there is no capital S, so software is limited. And basically, during this project, we did a number of things. We discussed first the certification schemes, because we think that they don't take into account invasive attacks properly, and that open silicon will be heavily penalized. So the rules can be changed, maybe, so that's just food for thought. We did work on countermeasures against invasive attack, but we published them because we think a good countermeasure is something that I can show to you and say, good luck if you want to bypass it, that would be good. And then we did a number of things. So the main thing now is hardware Trojan detection. And I think you all heard about this, And the main issue will be to get like a golden sample. Okay, so you can say, yeah, we can do a side channel to see if the sample is the genuine one, the genuine design. You will have some issues because you don't know if you will cover all of the possibilities to trigger the backdoor and stuff like this. So it's difficult. The way we would do it at Explain, of course, would be to reconstruct the mask and to compare this with the original design. The good thing with open source design, well, the mask should be open source. Okay, so if I have the mask, it's the golden sample and I can compare things with it. And that's the goal here. Oh, this is scary. Anyway, okay, so, okay. The idea is simple. I can speak without the picture, but it's less entertaining for you. All right, so the idea is simple. This is what we will do. Taking a chip, deprocessing, imagery, mask reconstruction, comparison with the original mask. Of course, we will do this with the lab, with ChipJuice, reconstruct the mask, and basically, if it works, if you make a difference between the original and the reconstructed version, should be the same thing, okay? You think this is the important phrase. Do you think it's going to be this easy? I think you understood that the answer is no. And basically, here we are. So the initial plan was to use, in the consortium of the European project, somebody was designing an open source design. So we did work on it, but unfortunately didn't get the chips in time. So this is where I need to thank Tiny Tapeout because they gave me chips. Their designs are open source. So I have GDS2 and chips now, so we can work. And the reality is that we came across a lot of difficulties. So here is the list also of all of the victims. Rest in peace, STM8, some closed source secure elements and some other like chips, because we needed chips to experiment basically. So yeah, depending on the size, the tech node and all this kind of different properties. So we used a lot of them. Sample preparation. This is a terrible example of a bad sample preparation. You see the side of this chip? There's no more information on it. That's called side effect, and that's come from polishing the chip. If you deprocess using polishing only, good luck, you will fail. So you need to use different techniques, and the techniques that we have been using for the project was wet chemical etching, dry chemical etching, and of course polishing, but mixing the whole things together, right? And if you want to validate or to verify the supply chain, you must be fast. So that's why we worked on the process. The idea was, at the end of the day, we should be able to reach all of the layers of a chip using one chip only. Okay? So this is still difficult, to be honest. But anyway, so here is chips that are ready for deprocessing, and to avoid the side effect, you can put on the side a piece of wafer. All right, it will minimize the thing because there will be not a gap between the chip and nothing, and the polishing disk will not start hitting the side first. So it's better. It's not perfect. So then I said, okay, let's put pieces of wafer all around the chip, And the truth is, it's difficult to place them accurately. So okay, let's fill the gaps with epoxy. So you need to find a good epoxy that will resist the chemicals, the high temperature inside plasma etchers and stuff like this, and that have the right, I would say, hardness. Okay, not too hard, not too soft. Must be kind of similar to the chip. Would be ideal. At the end of the day, the silicon pieces are useless if you put epoxy anyway. So epoxy only, and this minimizes the area that you will polish, so you're faster. And remember, that's one of my targets: less chip, faster deprocess. So that's what we did. And the fact that we used epoxy was also good because the plasma etcher that we have, at least, is not isotropic. No, it is isotropic. It's not anisotropic. So the side of the chip would be eaten first, and your chip will shrink in size, So there's an easy trick to avoid this. You can put a marker pen and just color the side, it will protect the chip well enough, but this is better. Okay. So on this picture, 2 layers have been removed. No side effect, it looks cool. So that's pretty pretty much all that I want to share for sample preparation, but there are so much more parameters that you need to take into account. We did great, so we did good progress on this. But the big part was the image processing. All right, so this picture, that's a STM8 digital circuitry, 30,000 cells, 450 megapixels. Okay, so that's a big picture, and guess what? The SEM will not take the picture at once, so that's probably 1,800 pictures already. So now we need to stitch pictures together, and that's going to be one of the main issues, okay? You want to compare a mask you extract from this with something which is perfect, so this needs to be perfect. Pixel-based correlation versus feature-based correlation. Just an example, those are optical pictures of a very tiny area of two chips that are basically the same. If you put one on top of the other, guess what? Doesn't line up. Right? So distortion will be there. Okay? And that's the point. We will need to take into account the fact that every pictures we are taking will be distorted, especially with the scanning electron microscope. Still better than a car, but you know. So 3 different alignment methods were tried. The first one, easy. You take the two things, pictures, and also the mask, and you put reference points to align the reconstructed mask to the other one. Good luck, eh? It's big, it's long. So we fail on the target of being fast. So this is not the good method. Second, you say, okay, you have features on the 2 layers. So basically you can write an algorithm that aligns the features, right? So you can do this, but you will still need to manually check. But this looks not too bad, you know. So I will keep this in mind, you know. I call this gridless mode. In ChipJuice, you will understand why. Because there is another strategy, this one, which is basically to extract features, but the features of the IC will be placed on some kind of a construction grid. So if you can recover this construction grid, that's a map of the distortion. Okay? This grid should be perfect. On your pictures, it will not be. So it's a map of the distortion, basically. So it means you can correct now the pictures to remove completely the distortion. And that's basically what we use, because now if you look here, you will see that here you have 3 layers at once, and everything is like pretty well aligned, I would say, because the construction grid for the different layers, well, they match, it's the same. Okay, so instead of trying to align features or pixels, now we are in a different coordinate system, which is the grid itself. Okay, so I would say this solves one of the problem. So now we can align the construction grid of a genuine GDS2 file, the mask set, with the reconstructed one. Okay, so it would be great to be able to compare the features now. This being said, using this grid system makes it possible to scan the layers with different magnification, which will make you save time, you know, because on the upper layer, there's not so much going on, so low magnification. On the bottom layers, there will be a lot going on, high magnification. So now you save time on the upper layer, which it was one of the objective, so why not? Okay. Here is a picture where I did the 2 extraction, grid and gridless, so with the grid and without. And here I put the 2 on top of each other. You see like those little squares everywhere? That's basically the gridless mode warping parts of the pictures. So the gridless alignment strategy number 2, not good enough. Okay, so we will stick now with the grid version. Fine. This is where the chip arrives. So that's the chips from Tiny Tape Out. So I think it's an MPW2, but I'm not very sure. It could be MPW3 anyway. So you see the chip with the RDL layer, a redistribution layer, and the balls. Okay, so that was one of the targets because we could compare the pictures with the GDS2 this time. Okay, so we deprocessed it, removing the RDL and removing all the layers. We stopped at M1. This is a picture of M2, and basically the layers were processed using our tools. So you can see on on your left side the original design, okay, the GDS2 file, and on the right side the same area, but it's the reconstructed design. I don't know. At your distance, it might look good. It's not really good. If you really look closer, you will see that the shape of the polygons that were found on the pictures are a bit crappy, you know, so things doesn't really align, you know. So if you start to make a difference, you will have glitches everywhere, you know. You say, oh yeah, maybe there's a backdoor here or not, and that's not what you want. So that was the next stage. We can align the grid. Let's make features good again. So it should look like this at the end of the day. Straight lines, very nice edges and stuff like this. So this is where I want to use the keyword machine learning, because it seems that in tech we have to do it at one point in our life. So I checked the box. That's fine now. The thing is, we have a lot of SEM pictures. I've been looking at chips for the last 20 years. So that's a lot of pictures. That's a lot of extracted features. Maybe they are not so great because, in fact, the pictures were corrected, but the goal was to remove short circuits or open circuits, not to have very nice lines and stuff like this, you know. So, But you know what? We were thinking, if you have enough data, you know, maybe it will average or something, you know. So let's use a network like UNet and do the thing. And then that's frustrating, I would say. For via detection, using a neural network, that's super nice. It works all the time, you know, but maybe you don't need it, you know. Okay. For the track detection, where it's a bit harder, it's very easy to match the result of the shitty algorithm that were used before. Shitty is a big word. I don't like it, but you know what I mean. The not so nice algorithm. But to learn the network to have lines that would be centered on the grid, that would have the right shape and everything, is a different story. Again, I'm not sure you see it properly here, but the solution that we've been looking for was basically to restart from the beginning in a way, you know. So we took all our pictures, but now we have we know two things. We know polygons, so the features, the tracks of the integrated circuits, but we also know where they should be placed, you know. So this grid thing. So first of all, the via, very easy. You align the via on the node of the grid. So now they are like inside the GDS2 file. Same thing. They are aligned. Distance accuracy. Okay. For the tracks, well, you do the same thing. You check intersection of the polygons with the grid, and now you know where the tracks are on the grid. So you can realign the track on the grid, give them a proper width, and all the angles will start to be correct. So at the end of the day, the extraction that you will do will look like this. So you can see before and after. I think the after is better. The cool thing is then, so we post-processed all of our pictures, which is taking time, you can guess. Then we need still to review them. But then when you train a network like UNet is like an encoder and a decoder, but the decoder part can learn this kind of things, you know. So it starts to make things straight and everything. But then you can still post-process the result of the semantic segmentation. That's another complicated word. I did 2 today. And then you have super fancy results. So now, if you look at the genuine mask and the reconstructed mask, the grids are aligned. And now the features are aligned on the grid. So basically, if you make a comparison of the two things, you know what? I think it's going to match pretty well. And that's what we could observe. So I think it was mission accomplished in a way, you know. And we had side effects that were not expected. So I don't know if it's visible on the picture with the grid so much, but on this one, I can show it. There was a defect on the picture. Okay? So it was detected as a track, but this track is not grid aligned. So basically, what the post-processing is doing now, it's removing the AR by itself. It says, no, that's wrong, shouldn't be here, you know. So we get this, and we were not thinking about this, but it's a cool way of making a correction in netlist. You need to see that on one layer of a chip, how many tracks do you think you have? You have millions of tracks, you know. So if you can have something that corrects the result for you, it's a win. Okay, so I take it. Anyway, I come to the conclusion that you will see. I will still let the topic open in a way. If we are in the open silicon context and you can get the mask file for the design, I would say it's fairly easy now to make a comparison, so to check for added circuitry or removed circuitry or altered circuitry. So that's something that you can do. So supply chain verification is a thing, okay? The process, I mean, like for to explain at least, that was also, I didn't say it, but that was also my motivation, you know. Everybody was heard, I think you all heard about this process. Okay, let's compare the mask, you know. But it's not something easy, but now it's demonstrated, it's okay, you know. If you can find the reference grid, now you can do whatever you want, it's going to be just perfect. The thing is, it doesn't stop here. Let's say now that you have a difference between, so I can tell you one thing, the tiny tape-out chips are backdoor free. So if you want to build your own design, you can do it safely. That's okay, you know. But let's imagine the case where you find a backdoor, or maybe you have like extra circuitry, like on this picture. Well, on this picture, the extra circuitry, you can extract directly a netlist of it. So basically, you can simulate the backdoor. And this is something you will never be able to do with a side channel where you will say, oh yeah, I think there's a backdoor there. But then what, you know? Then you call somebody to reverse engineer the chip, and but this method will give you access directly to the backdoor, you know, and you can simulate it, characterize it, and say, okay, it's a backdoor or not. I mean, like, then the rest is different. Teaser, because I said everything we will see today will work only with open source silicon, and the reason for it is like I don't know any chip vendor that will give me their mask file. Okay. If I call NXP, Infineon, ST, I mean, you name them, you know, and I say, can you give me your mask so I can compare for a customer? They will just laugh, you know. They don't want this to happen, okay? But in the process of what we've been doing, we found a solution to this. So there's a solution. So it's a teaser. I'm not telling you the solution, you know, like this patent thing where you can say a lot of things, you know. And we are looking for basically designers that would like to invest a bit with us in the solution. But there's a solution where the chip vendor will not have to give the mask file to you, and you can still assess if the chip is backdoor free or not. Maybe, you know, somebody can come back to me after, and we can continue on this. I need to thank all the partners, so all the TechSplain team first, all the partners of the Arshin project. We are doing a summer school in September in Greece. So if you want to learn more about what's happening there, you know, or if you want to go to Greece for vacation, you have the website here. You know. I also want to thank the Tiny Tape-Out team, you know, because they gave us enough chips that I could kill all of them in the lab, get nice pictures, make some research, and that was really cool. This being said, I thank you, and if you have any questions, I will be very happy to answer to them.
Thank you, Olivier. We have time for many, many questions.
I was speaking fast.
Hey man, how's it going? I read a paper many years ago on introducing backdoors in silicon simply by changing the doping under some of the gates and not actually changing or adding anything to the netlist. You hadn't mentioned it specifically, but I was curious if you're actually adding the doping layer to your reversing.
So this is taken into account because basically dopant modification is something that you can make visible. Pictures are not lying. That's the cool thing about looking at chips. I like when people are saying we will prevent reverse engineering. I would say good luck because all of the countermeasure will not work. And if you modify the dopant, you can. You have chemicals that will each specific dopants type. So you make them visible. You make the difference on your pictures. Yeah.
All right. More questions.
Question about the reconstruction. The layouts you shown, they seem to be, I'm guessing the aluminum metal because I don't see any dummy metal on the layouts. So as you know, the modern devices made with the copper conductor technology, all the empty areas of the electrode, they filled with the dummy metal. How does algorithm deal with that?
I mean, that's okay and not okay at the same time. I think on some pictures you see some of those dummies, I call them spacers or fillers. Let's say fillers, I think would be the name. And the sad thing is usually at the design stage, you don't have them on the GDS2 file. So then you make the reconstruct the file, and now suddenly you have extra features. But those features are not connected. So this is how we can filter them out, because it's dummies, basically. So you look for they are going up or down, they don't exist, that's a filler.
For all your pictures, what process node have you gone down to?
Sorry?
What size have you gone down? What geometry?
So we do a lot of forensics analysis. So basically, the chips we are looking at are secure elements and stuff like this. I would say from 40 nanometer to bigger. We have a project now going on where we are looking at 22 nanometer. I mean, why not? Yeah. If you look, we did everything with wet and dry chemicals and CMP. So it's very like old school. I would say. For modern tech, I would rather use like a broad beam ion milling machine, for example. People will speak about plasma FIBs. I think it's some kind of a scam. I mean, I didn't try it myself so far, but I would go BBIM. The thing is, if the chip vendors can manufacture the chip, there will be always like the tool to make the failure analysis. So maybe I can't do it, but that's still a risk.
So for this process, you're comparing back to a mask that hopefully a supplier believes they've manufactured from. How are you confirming that that mask matches the original logic design and they haven't had something injected before that point?
I can't do this. I think that's a simple answer. The best I can do is going myself to the fab to try to get the mask. Or you know what? You can also reverse engineer the how is it called? The reticule. Do the same thing, You say, okay, what was the mask that was used? And then you can check the reticule against the mask, and then the chip against the reticule, and then it's good. But yeah, the reticule is way bigger, so it's fine. I'm pretty happy to do this. It would be like reverse engineering PCBs. So yeah.
All right. Are there any more questions?
You talked about reverse engineering to get these nice image diff masks as opposed to just doing a logical comparison. It seems like a logical comparison would skip a lot of trouble and uncertainty. Is there a reason why you chose one over the other?
Yes. The reason is pretty simple. I want, at the end of the day, people will need to market something like this, and somebody will have to pay. Okay. And full reverse engineering of chips might be expensive, but what will be your confidence level if already you can validate the local interconnect? Okay, so you don't have like the net list or the diagram yet, but you say, okay, all the local interconnects the same. Backdoor, no backdoor. It doesn't mean there's no backdoor, but you can have like different level of confidence.
Thanks for your talk. If I call my wife, can you tell her that I need a SIM?
Of course.
Yeah, okay, good.
Of course. You need a SEM. SEMs are cool.
Can you talk about the overall cost to go from zero to your end conclusion, if possible, for other labs that would be interested in replicating?
I can. It's the question is so complex, So this is how we would do. At least for explain the way we code things is the following: we want first to know the tech node, the surface area, the number of layers, because then we can plan the deprocessing and the imagery time, the reconstruction time, and so on. So then tell me those parameters, and I can give you a very precise answer. If you don't, it's ranging. I mean, this whole work would take between, I don't know, let's say maybe a month to no limit with the time. If you ask me tomorrow to do this on a 7 nanometer tech, 16 layers, 1 square centimeter, I don't have the right tool to do this in an efficient way. I mean, like cost effectively. And I'm speaking about SEM, for example. Zeiss has like some cooler things for the situation.
So you said that the technique has applicability only when you have a golden sample and under the assumption that you have known good to start with, and then you teased us with, oh, but I think I figured out a way for things where they won't give me a golden sample. Why would the solution not be basically just check a bunch of chips from a bunch of places bought in different places around the world and with some probability, unless every single chip in the world is backdoored?
No, that works. I agree with you. You can do this. You can rely on statistics. You say, okay, I did like reconstruct like 100 times this mask, and out of this 100, 100 were the same, no backdoor. That would be simple. Or you say, I found 3 times something different, and rely on this. Why not? Yeah.
Okay, and so then the question is your other alternative solution somehow non-statistical? Like, are you claiming you have some other solution?
Yeah, it is non-statistical. Yeah.
Okay.
Any more questions? I'm sure Olivier is going to be around if you want to ask later. But for now, let's thank the speaker again.
Thank you.